I started to find MIPS SMP machine for suitable to implement SMP. Then I found Broadcom Cyber BCM1250, and looks nice. It is kind of SoC. It has 2 core of 1 GHz MIPS 64 and supports DDR3 gigabit Ethernet, PCI, and hypertransport. So it's very high spec. And I realized Cisco 3845 integrated this processor, but the problem was price. It's over 47,200, so it's totally unacceptable. I can't buy it by myself. Then I try to find another device which is more reasonable price. Then I found out some antique SGI machines are available on eBay. These are basically very cheap. And I realized SGI Octane 2 had 2 cores and already supported by OpenBSD. That means not SMP but in-processor are supported. And the price was just $33. It was really reasonable then compared to original price. This is my Octane 2. It had 2 core MIPS 2400 MHz each, 1 GB SDRAM, 3D graphic card, integrated with audio, 35 GB SCSI SBB, HDD, 100 BSD Ethernet. And I opened it. Actually, it's the other machine. It's Octane, but not my Octane 2. The little bit different model. This one is CPU module. It's integrated 2 processors. And here is a memory module, which is probably 520 12 megabytes each. I removed it. Then I opened it. Here is 2 cores of MIPS 10,000 processor, and these have 2 megabytes L2 cache each. It also has power module. It's here. If you want to see near, you can come here later. Zoom up. It is manufactured by NSC, named VR10000. Right, then return to the story. And I started working on Octane 2 since April 2009. Then I wrote about, on my blog, I wrote about progress and some codes or patches. Then Miot Bart, who is working on SGI port and also OpenBSD core, he discovered it. Even my blog was written in Japanese. Then he suggested to my code be merged into OpenBSD main tree. Then I accepted it happily. Then I became an OpenBSD developer in September 2009. Then I started merging the code and joined Hardware Hackathon, which held in Coimbra in Portuguese. I work with Miot and Joycing. Joycing is the another guy working on SGI port. And now it works. We merged into OpenBSD main tree already, and you can try it now. If you have Octane, unfortunately, it seems stable. I tried make build again and again over a day, and it still keeps working. I'll show you the demo. I couldn't bring real my Octane, so this is just a movie. And I captured serial console of the Octane 2 by my MacBook, and I show it. This is a firmware console of Octane 2, and I executing HM command, which shows the hardware spec, and you can see 2 processors and 1 GB memory, HDD network. Then boot it. Here the bootloader was in the kernel, and the kernel detected 2 CPUs, CPU 0 and CPU 1, you can see. And it's scanned in the SCSI bus, and we can see 35 GB SSD here. And it's still scanning SCSI bus. It takes time. And here IOC 0 is Ethernet controller, and here are the 2 serial ports. And now it's mounting file system. Starting network, execute a DHCP client, and launching daemons. And now we can log in, and I logged in and executed top command. And here we can see 2 CPU statuses and CPU usage. Then I will open the another console and log in same machine via SSH. Then I compile the kernel with make J3 option. Alright, I execute it, then switch back to top command console. Yep. And the CPU usage will increase, maybe it will increase over than 20% gross processor. Yep. And here you can see CC1 executing on CPU 0 and the another CC1 executing on CPU 1. So that means these different processes are running concurrently on the different processors. Demo is that's it. Back to the slideshow. Then I measure the performance of kernel build, and I compared uniprocessor kernel and SMP kernel, and I executed make J1, make J2, and make J3. Then measure the time by time command. So the unit is second. Actually, it takes huge times, but on J1 there's 4% of overhead compared with uniprocessor kernel and SMP kernel. And on J2, or maybe similar on J3, there was 40% of speed ups. Then I compare this benchmark with Intel machine. Here is the result measured on AMD64 architecture. The machine was Core 2 Duo machine, which also had 2 core of CPU. On this machine, it was the overhead was 2%, and the speed ups on J2 was 44%. In fact, the compile time is very much faster than Octane. It was on J1 1600 seconds, and here just 250. But the percentages of speed ups or overhead was a little bit similar. So it's just a kind of very basic benchmark, but maybe it shows us our implementation is maybe working fine, and the performance is not so bad as I imagine. Then what do we need to do for the SMP work? There were lots of work, and I wrote these things in my paper. Maybe you have one and you can read it, but I haven't enough time to describe all of these details, so let me describe it more simply. And I suppose we can classify tasks into three kinds of problems. These restructuring per processor informations, implement and lock atomic implement and use lock atomic primitives, and other related problems. Begin with restructuring per processor informations. In the original SGA code, some information which related to the processor are allocated only once, and it's shared between the processors if we use it on MP SMP code, so it is MP unsafe. On simple case, the information is stored into global variable that means allocated only one. Then how can we solve it? It's very simple. Just move these variable into CPU info, which is per processor structure, and that's it. But on complex case, in PMAP, which is a hardware-dependent part of memory manager, we need to maintain some information, not just per processor, but per processor multiplied by per process. So we cannot solve it, just move it into CPU info. Here is the simple case. This code is part of proxy, which is in SGA code, and here is clock interrupt handler code, and part of it. And here is three global variables, which name CPU counter loss, CPU counter interval, and pending ticks. These codes are maintained and calibrating next clock timing, but the clock controller is integrated on the CPU, so we need to manage these variables per processor to be MP safe. So we just move it into CPU info. CI is CPU info pointer. We can fetch current CPU pointer info by curl CPU macro, which actually I implemented for the SMP implementation. Now we can access these variables through CI pointer. Now it's MP safe, so it's very simple. But there's many such a code. Then we rewrite this code even in some assembly code. The problem was the complex case on PMAP. I have to describe some detail of MIPS TLB spec because it's very tightly related hardware. MIPS TLB entries are attacked with 8-bit process ID called SID. It's used for improved performance. MMU skips different process TLB entries on lookup. How can it do that? Is the MMU knows which process running on the processor, because the CPU tells current SID to MMU, then they can know that. So it simply skips the other processes TLB entry. Then we won't need to flash TLB entry every context switches. And we need to maintain process versus SID assign information because it's smaller than PID. It's much smaller than PID because it's just 8 bits. So we need to use rotated if SID needs to FF to then flash entry, TLB entry, then use 1 again. So we need process versus SID assign information on the memory. Then this information should keep beyond context switch because we may have TLB entry after context switch, beyond context switch. So we need to keep it. And on SMP implementation, we have main processor and we should maintain SID individually per processor. So what we need is SID information per processor multiplied by per process. This is a part of code in PMAP-C, and original and modified code. And here is TLB PID count, which stores new SID assign information. And if new process will create, this ID will assign on that process. And here is PMAP. PMAP has memory information, page table information of this process, and it has field named PMTLB PID, which stores current process SID. Then how we related it is related is an array TLB PID count related as an array, then accessed by CPU ID as its index. So now we have information new SID per processor. Then here PMAP itself is basically per process, and now PMTLB PID is related as an array. So we have SID as information not only per process, also by per processor. This is what I said. The information managed by per process multiplied by per processor. On the different topic, implement and use lock atomic primitives. We needed to implement these primitives, such as lock primitives. Lock primitives we implemented mutex, nplock, and some others also. nplock is used for giant lock. OpenBSD relies on big giant lock model. Then we need to implement to use this kernel. We also need to implement some atomic primitives. In fact, there was already some atomic primitives on original SGR code, but we needed some more. Then I added compare and swap function for 64-bit atomic at or something like that. I added more info, and we not only to need implement, but we also needed to use some log primitives in the nothing dependent part. We needed to occur in giant rock prior to entering the kernel context, because as I said, it's using giant rock model. And I acquire giant rock on hardware interrupt and software interrupt and on trap. This is a part of code. It is clock interrupt handler again in the other part. And this handler may call hard clock if CI pending ticks is not greater than 0. And hard clock may change shared data in the kernel. So we need to acquire giant rock before calling hard clock. Then we replace it after called hard clock. So we added NP lock here and unlock here. But it causes a bug, and I describe the bug later. And the other topic, hardware-related problems. Actually, SMP implementation is basically hardware-related. We introduced three kind of problems, such as spinning up secondary processor, keeping TLB consistency by software, and cache coherency. We need to run secondary processor before we use it. How to do it is access hardware register on controller device. Controller means NP controller, secondary processor's controller. Then power on the processor. After power on the processor, we of course need bootstrap code. We need on bootstrap code. It has to be similar to primary processor's bootstrap code, but we won't need kernel initialization or memory initialization or device initialization because the primary processor already did it. So all we need to do on secondary processor is just initialize secondary processor, then fetch the new process to be running on secondary processor, then run it. The other topic, keeping TLB consistency by software. MIPS TLB doesn't have mechanism to keep consistency. So we need to do it by software. It's not only MIPS problems, it's just like the other typical architectures. And we do invalidate or update other processors TLB using TLB shutdown mechanism. It's implemented by IPI, which is interprocessor interrupt, and some software code, and cache coherency. In fact, MIPS R10000 or 12000, which is a processor for Octane or Octane 2, which has full cache coherency. So we don't have to care about it on Octane, so we didn't care about it on our implementation, but some other processors, including some MIPS, SMU processors, haven't full cache coherency. If so, we need to maintain these problems with this software, just like TLB and with consistency. Then I talk about ideas implementing our SMP implementation. We have faced a number of issues for implementing SMP, and I will talk about some of the problems and the solutions, such as fighting against deadlock, dynamic memory allocation without using virtual address, and reduced frequency of TLB shutdown. First, fighting against deadlock. It is hard to find the cause of deadlocks because both processors runs concurrently, and it causes timing bugs. Conditions depend on timing. It's both processors' timing could be, and we need to be able to determine what happened on both processors at that time as the deadlock occurs. And there are some tools for debugging it. First one, JDataGuides is very useful for debugging. We can get any data for debugging on desired timing. Desired timing means every time, even after kernel hang or crashes. So it is the hardware, kind of hardware, and it's directly connected to the CPU. We can fetch any data, and we don't need to kernel arrive. And I use it when I was implementing SMP for the embedded OS. So it's usually for the embedded system or just for embedded system. So not for SGI workstation, not for Octane. So there was no way to connect to Octane. So I didn't use it for the implementation. Then we have DDB. In OpenBSD kernel, it has in-kernel debugger named DDB. We can get similar data for JDataGuides, but the kernel needs to avoid, because it's just a part of the kernel, it's software. So if the kernel freezes, there is likely no way to execute DDB and debug it. And there is also some problem. There were missing features. It is part of SMP implementation. Because we didn't implement SMP, we hadn't machine DDB CPU command, which is processor switching function on DDB. Without this, we can only debug one processor which invoked DDB on a breakpoint, or occurred panic on that processor. Then we can get that processor stack trace or register done or something, but we won't debug the other processor. That was the problem. So if I try to implement this command, I cannot debug by DDB to implement this command. So it's useful, but not always useful. Then finally, we use printf. It's most popular kernel debugging tool, I guess. So just like printf on new code, easy to use. There was also some problems, unfortunately. Printf wastes lots of cycles, changes timing between the processors, so we may miss timing bar because of it. For example, there was some deadlock I found it. Then I put many debug print in a kernel, then deadlock will disappear. So it could change the timing, then we may miss the bug because of it. Then some point of the code in the kernel printf and safe. Then it causes kernel harm. So if I will put the printf, suddenly kernel doesn't run. So there was problems, but we use it anyway because we have no other choices. Then I realized there are two serial ports and two processors. If I just write printf, only primary serial port says some messages, but the other serial port doesn't do nothing. So if we have lots of debug print, it is hard to understand which line belongs to the what processor, and we get confused. Even I print the number of the processor in a line, then I implemented dirty have code which outputs directly to the secondary serial port, then combi printf. Then I realized debug print. The primary processor outputs primary serial port, and secondary processor outputs secondary serial port. Then what do we need to print for debugging SMP anyway? I started to know where the kernel running. And I put many debug print everywhere in a point kernel main running through the point. And after user run started, that means spin init executed. It is fast process. I enabled syscall which dumps all system code. This one is very useful using with this debug hack. Now we can get a two console which shows which processor running the what system code or what process. So it was very useful for debugging. Anyway, how can we determine data point? Just using printf. Deadlocks are occurring on spinlocks. Spinlocks loops permanently until a condition becomes available, but that condition may never comes up, so we call it deadlock. And at least to know which lock primitives we are stuck in on, we need to stop permanent loop, by implementing timeout counter and print debug messages when it's stuck on the loop. And here's a very simple timeout counter code. It is for debugging. It's mtx and which is mutex function. This code is on OpenBSD SQL. It loops permanently until try lock function succeeds, then return 1. If it's returned 1, we can store some information in the structure then return, but if it doesn't happen, we will loop forever in a loop. Then I added I and I increment it. Then if it's become greater than mtx timeout, then execute panic. And we can know these primitives causing the panic, but this is not enough to determine what exactly happened in a kernel. why it's not enough. Here is the deadlock image. CPU A acquires lock A first, B acquires lock B first, then try to acquire another lock, then stuck, then deadlocked. We can break here. If is permanent group, then we can break by the timeout counter just I show you. But here we may get a stack trace of on CPU A, or we can get a return address of CPU A, but that is not the complete information, because we also want to know which function acquires this lock. Then we cannot get information from here. Then I added some more code from here. I just added this is a built-in function, which is built-in return address. Then I stored that address into this block structure. Then if the kernel causes timeout, it's deadlocked, I printed out that address. Now we can know which function acquired the lock on CPU B, and also we may know the function which tried and failed the acquired lock on CPU A, because we just to do that, just put the built-in return address here too. Then we can know both acquired the function. Then use these techniques. Then we found some deadlocks. This is one of the deadlocks we found then solved. On CPU A, which caused the fault in code swap, then it acquires giant lock because we need it on this kernel. Then it decides shoot down TLB entry on CPU B. Then it will wait until CPU B invalidated that TLB entries, but it will never happen, because at that time CPU B interrupted by the hardware interrupt. Then the interrupt handler disabled interrupt here. Then it is hardware interrupt handler, so it also tried to acquire giant lock. Then it spins here permanently, then never accepts IPA interrupt. So it caused the deadlock. Then how can we remove it? We just re-enabled interrupts. We renamed interrupts IPI interrupts only here. Then try to acquire the giant lock, and it won't succeed, but in here CPU B now can accept IPI because we enable that. Then we can execute IPI handler, then invalidate TLB entry, then return ACK for CPU A. Then CPU A can finish TLB shooter. Then it will release giant lock, then return to the previous work. So now CPU B can acquire giant block, then it also can finish the work. Then the drop will disappear. So the solution was just enable IPI interrupt on the interrupt handler. The means enabled interrupt before occurring giant block. So we also had a same problems, not only hardware interrupt handler, but also software interrupt handler and trap. So we added these calls, all of these functions. Then this is the sample of the fixed code. And this is the same code I showed there before, which is clock interrupt handler, and it's for hard clock, so we lock giant lock here, then release it here. And so this NP lock caused the drop before that, so we enable IPI, and if we enable interrupt and change interrupt mask here, we may need to save the status register before doing that. So we set status register which has interrupt enable bit and interrupt mask here, then restore after released giant lock. And that's it. It was a word. But it also happened on we called SPL high. So here is same problem. SPL high is highest interrupt priority. Interrupt priority level. Yeah. And it masks all interrupts, including IPI, and we will lock there. Then we can solve it by using enable IPI, just I showed you, but we use the little bit different solutions here. We define new interrupt priority level named IPL IPI, and to be higher than IPL high. Now IPL IPI is highest level, and the IPI handler never masked by IPL IPI. So if even we call SPL high, it will not mask IPL interrupt. And this is the code. Just define IPL IPI here higher than IPL high. The other topic, dynamic memory allocation with using virtual address. To support arbitrary number of processors that could be 2 processors or 4 processors or 8 processors, but we never know that until kernel detected the CPUs. So to do that, the CPU infrastructure and the bootstrap kernel stack for secondary processor should be allocated dynamically. We can allocate memory dynamically just using malloc, but the malloc returns virtual address, of course. We can't use virtual address for them. Well, we can't use virtual address because stack may use before TLB initialization on secondary processor, then it will cause the processor fault, so it will die. And also, MIPS has software TLB, so we need to maintain TLB by software. I mean, the MMU itself never know where is the page table or how can we fetch the entry from page table or something like that. We have to handle it by the software on kernel on OS. So the TLB mishandler is the code to handle it. It is in a part of the kernel code. This handler refers CPU info, which we want to allocate dynamically, and we need to store some information that related with memory management, because we wanna manage this information per processor. But if this CPU info is virtual address, the TLB miss handler calls TLB miss. Then TLB miss handler calls TLB miss handler itself, then got a infinity loop. So we can't use the virtual address. Then to avoid these problems, we implemented worker function to allocate memory dynamically, then get the physical address, then return it. Here's the worker function, and here's a condition. The memory chunks, if it's smaller than page size, we just allocate memory by malloc, then get a virtual address, then extract it to physical address, then return it. But if the memory chunk size will larger than page size, we need to alloc pages continuously. We need continuous pages because we will use physical address. To do that, we use UL and PageRest alloc. Then get the first page and get a physical address of the page, then return it. Then the other topic, this frequency of TLB shutdown. There's a condition. We can skip TLB shutdown and invalidate or update. That means we won't need TLB shutdown every time we invalidate or update the entries. On kernel mode, it's due to the hardware implementation or could be kernel implementation. We need to invalidate. We need to shoot down every time in a kernel mode. But in user mode, if shooty processor doesn't using the page table, we won't need shoot down. We just changing SID assign for this shooty processor is enough. And if we don't share the page table between the process or we won't use native max thread application, usually the other processor, shooty processor, doesn't using the page table on the user mode, this process. So we usually won't need shooter. But in reference PMAP implementation, which from FreeBSD MIPS, we reference the FreeBSD MIPS PMAP-C. The TLB shutdown performed non-conditionally, even in a case it isn't very needed. That means this case. Then we added the condition to reduce frequency of it. This is the part of the code from FreeBSD MIPS, and this function to invalidate the page. It runs on shooter processor, and it's just called SMB vulnerable. It is TLB shutdown function. It's just shoot down every shooty processor non-conditionally, and it tells shooty processor to execute PMAP invalidate page action function, and shooty processor execute this. In kernel mode, it is that condition. It's just invalidates the page and return. And in user mode, in this condition, it won't invalidate the TLB entry. So in here, it's invalidating that this condition it just return or just changes SID assign information then return. So we move this condition to here, and this is the current implementation on OpenBSD SGI, and this whole code is runs on shooter processor before executing TLB shutdown. In here, it's checking if this condition is on the shooty processor, and if it matches, then we want add a bit to CPU mask variable. Then check CPU mask is not 0. Then execute TLB shutdown for only this processor. So now we could reduce the TLB shutdown. And finally, FutureWorks. In fact, I wrote Machine DDB CPU just before Azure BSD Hackathon, and I didn't committed it yet, so I will committed it that. Then I also have interests with Cavium Octeon, which is MIPS64 processor, and it has 2 more cores. It's SMP chip, mainly used for routers. So if it's acceptable for OpenBSD project, I want to make new ports. Maybe I will work on SMP support for SGI Origin 350. So maybe gives me that. Yeah. And I'm also interested in machine independent part of SMP, such as native thread. It can use on OpenBSD, but even on Intel architecture, it is not enabled by default, and it looks haven't much performance. So I'm also interested in it. This is the end of my presentation. So, do you have any questions? Yeah.
So, did you consider porting Witness from FreeBSD to try and diagnose your deadlocks? There's actually a whole system that exists to help you with that you could have used.
And so
you know Witness?
Witness? Don't know.
Okay.
Don't know.
Something you should look at. And why wouldn't the Cavium be acceptable to OpenBSD?
The main factor in OpenBSD is as long as enough people have them.
Okay. But it's hard to get?
Yeah. No, I don't know. As long as enough people have them, then it's worthwhile.
Okay.
If it's a single embedded board which only one person has, then it eventually is code that breaks and rots. And then people do a grep through the tree for a particular thing to fix, and they run into something which they can't maintain. So we try to ensure that I don't want to.
Okay. Okay. So, other questions? No. Alright, so that's it. And thanks for coming.